and he will explain us something about variable resolution experiments using CAM-SE.
Thanks. Let me just acknowledge my collaborators first. Oksana Guba, Mike Levy, and James Overfeld, all at Sandia. Oksana and Mike are postdocs. Mike was a postdoc. He's recently moved to NCAR. So the motivation for this work is a relatively new project that has a goal by 2015 to develop a high-resolution version of CAM, Community Atmosphere Model, with improved representation of the hydrologic cycle, especially at regional scales, and running efficiently. And for CAM, that's around 5 simulated years per day on both DOE LCFs. That's both the DOE, the two type of supercomputers DOE wants to have by 2015. Our target resolution is 1/8 degree, about 13.5 kilometers. On these grids, we define that as the average number of degrees of freedom at the equator. I'm going to show some results where so we're using variable resolution as a test bed to develop, tune, and evaluate parameterizations at 1/8 degree. So I'm going to show some results where the multi-resolution capability is kind of a simpler problem. We can use it today, and we don't need scale-aware physics. We just need the multi-resolution capability to reproduce the behavior of the high-resolution model in the variable resolution region of high resolution. I'll try and explain that again when I get to it. So outline of the talk, 2 slides, overview of CAM-SE, that's CAM running with the spectral element dynamical core. I just have one example simulation looking at the global 8th degree model, comparing the results with the variable resolution simulation. So that's a global 1 degree with transition to about 8th degree over the continental US. And these are both AMIP simulations. That's prescribed ocean SST, but otherwise the full version of CAM. Then I want to talk about our tensor hyperviscosity formulation that we ended up using for unstructured conforming non-orthogonal grids, and I'll evaluate the impact of the unstructured grid refinement on the global errors in the shallow water test cases. So it's a little bit backwards, but we started with the AMIP simulations, worked on getting some issues fixed, and then went back to the shallow water equations to evaluate the changes we made to the model. So the overview of CAM-SE. CAM right now solves the hydrostatic equations using the hybrid sigma pressure terrain following eta coordinate. The dynamics in CAM-SE are modeled closely after the CAM Eulerian or the global spectral model, with the exception that spectral elements is used in the horizontal discretization. But otherwise, Simmons and Burridge, 1981 for the vertical discretization. Kinetic energy dissipation in the model, and almost all the dissipation introduced in the model is through hyperviscosity. And then in time, we use a RK2 second order, but M-stage time stepping scheme, and I'll come back to that in a second to explain that. It's, I think, a little bit unusual. For tracer transport, it's modeled after the finite volume version of CAM. Spectral elements used in the horizontal, but with a quasi-monotone bounds preserving limiter. And all the traces are advected with the mean flux from the dynamics to preserve tracer mass and tracer mass consistency. And then we use the vertically Lagrangian approach from S.J. Lin with a monotone remap at the end of each time step from the zero-cat limiter. And then the tracer transport to preserve the monotonicity properties of the horizontal discretization, we use a SSP RK2 scheme. So that's a 3-stage second order scheme. And so the choice of the stages here is designed so that the dynamics can run at the same time step as the tracers. So we determine the tracer CFL with this method, and then we optimize the number of stages in the RK2 scheme so that the dynamics, which is all explicit, sees the gravity wave CFL can run at the same time step. And typically we run 3 stages here and 5 stages in the dynamics because these type of methods have a larger stability region since they don't require the SSP property. The spectral element method, continuous Galerkin, finite elements with a quadrature-based inner product, so you get a diagonal mass matrix. So the whole thing is run fully explicit. It's the perhaps simplest possible finite element, Q3, Q3, Q for to denote quadrilaterals, 3 for polynomials of degree 3. The method is actually a QP, QP, but we typically always in CAM run with P equals 3. So velocity and pressure and all variables are all in the same space, a co-located A-grid-like method that's stabilized with hyperviscosity. It has a mimetic discretization, and we heard a lot about that on Monday. The spectral element method has those same properties within these co-located spaces, but in particular, div and grad are adjoints. The discrete divergence is discrete gradient are adjoints in the discrete inner product. Curl is self-adjoint. This gives you local conservation of any quantity in conservation. This is vectored in conservation form, like mass and tracer mass, and semi-discrete conservation of energy. And then we have this curl grad equals 0 property, which gives local conservation of 2D potential vorticity. Or another way to look at that is in the F plane, stationary geostrophic modes will be stationary. I never mentioned this. I didn't actually realize this property until I've been hearing a lot about it at the Newton Institute, but they're both, in a sense, follow from that property. So I'm going to show just an example simulation using these two grids. The first is our global 8th degree cube sphere grid. We have a very efficient and scalable configuration at this resolution. We've run it out to like 180,000 processors, but it's quite expensive. On Intrepid, it's a Blue Gene P machine at Argonne National Laboratory. It costs us about 6 million core hours per simulated year, and the typical allocation on that machine is about 40 million core hours. You can't run a lot of years, but we've run 2 years. The one reason it's so expensive is in CAM 5 physics is quite a bit more expensive than CAM 4, and we also are vectoring 26 tracers now. But this problem does run on that machine. And then we have our 8x regionally refined model. So this is 1 degree uniform with refinement down to 8th degree over the continental US. It's actually centered over the SGP ARM atmospheric radiation measurement site for other reasons for the project. And this one is much cheaper. I haven't run it on the same machine, but we can run this on our Linux, our institutional cluster at Sandia, and it costs us about 0.1 million core hours per simulated year. And this is just a close-up of that grid on the previous page. I'll come back to talk about this type of conformal mesh refinement. I just wanted to show an animation. I think the next one's the animation, and just an example calculation. This is snapshots from April in the middle of the 2-year simulation from the global 8th degree and the regionally refined. They're well into the simulation, so they're not expected to agree in any sense, except we hope the characteristics of the two simulations will agree in the high resolution region. In the high resolution simulation, you do see nice features that you don't see at low resolution, in particular detailed frontal structure and tapping of moisture. I'm going to paraphrase Phil Colella and admit I don't really know what any of those words mean, but it did come from Rich Neal, so I can assure you that it's an accurate statement. And then this will be the regionally refined. So the colors are precipitation. The gray is precipitable water, precipitation rate. Color gray is precipitable water, and the contour surface pressure and contours. And you do get in the summertime, you do get these nice convective systems with the isolated cells of convection that form and then propagate. in the high resolution region, you have a couple, and then the low resolution or the variable resolution model, we'll get a nice system when it loops around, develops in the region of high resolution and then propagates through the mesh transition region and diffuses out. So I'm going to let it go back around. So it forms quite near the edge, but the formation was fully in the high resolution region and then propagates through. So we've done a lot of work with this, comparing the climate in the variable resolution simulation with the high resolution simulation in aquaplanet mode and the climate, a little bit of the climate in AMIP mode. And I showed some of those results. I didn't want to show them again, but there are on the Newton Institute website from the first workshop we had a month ago. But if you're interested, you can look at that. But I wanted to comment on some issues we face with these types of grids. The initial runs showed a lot of precipitation artifacts in the transition region, stationary features that look quite unphysical. So we spent some time trying to smooth the grids, and it really had no effect at all on these kind of issues. And in fact, what actually eliminated the problem was a better treatment of the variable, the hyperviscosity, the coefficient of the hyperviscosity operator. So in particular, the dissipation of the model in the high-res region, we want it to match the dissipation, the coefficient that we use in the global high-res. And in the low-res region, of course, we want the coefficient of dissipation to be larger to match what's typically used in the low-res model. And then we'd like a smooth transition between those two values in the mesh transition region. And we've played around with a lot of different ways to do that. Diagonals, edge length, square root of area over the circumference, various things like that, and found things we liked, but it was kind of hit and miss, and we wanted to make this a little more systematic. And so what we ended up doing was using having to go to a tensor hyperviscosity coefficient so that you could specify the two length scales separately. That's where we got our best results. And the main advantage of using the tensor is when there are two length scales, so consider a rectangle like this. We don't actually have elements like that, but as an extreme case, if maybe a factor of 3 increase in resolution in this direction, and as opposed to the y direction. So if the resolution changes by a factor of 3, the hyperviscosity coefficient will change by a factor of 30. There's quite a large variation in what you want in the coefficient you want dissipating waves traveling in this direction versus this direction, which suggests the need for a tensor form. And then for these distorted elements, again, we tried to say what are the two length scales. And the one that worked best is to not use a geometric interpretation, but use the eigenvalues of the 2x2 matrix D transpose D, where D is the derivative of the map to the reference element. And this probably has a geometric interpretation in these kind of elements, but I don't quite know what it is. In an element like this, these two eigenvalues are the delta x and delta y directions, though. But if you use a tensor based on those two length scales, that's where we got our best results.
So that was just that plus the smoothness in the transition.
So the smoothness never had any impact.
No, but I'm saying that was.
Well, that allows you to get, so the two components are now smoother, right? If you use a single value, then you don't really know what to use in this.
So, but that's all you had to do. You didn't have to do any other smoothing of the coefficients. It's just whatever the grid gave you.
Right. Well, within an element, we make it bilinear. We don't allow it to vary in the structure of the element. So the lesson learned from our point of view is that in this method, the dissipation is more important than the actual grid. And I just want to say I think this is consistent with the results that Paul Ulrich showed yesterday from Ulrich and Jablonowski, 2011, where they looked at spurious waves at an abrupt 2-to-1 mesh transition region. And in the C grid, the spurious reflected waves can be grid scale, and so you minimize them by using smooth transitions. But in an A grid or collocated method, like spectral elements, the spurious reflected waves are actually at the grid scale, and so you can control them if you have effective control of grid scale waves. And if you're running a collocated method, you kind of have to already have effective control of these grid scale waves. And in the this week, and especially in the previous adaptive workshop, we've seen a lot of collocated methods that get away with a very abrupt 2-to-1 mesh refinement. All the DG codes and the MCOR Chombo finite volume, so all 2-to-1. In CAM, the spectral element version, it's of course closely related to DG, but we're using the conforming mesh refinement so we can preserve these mimetic properties. If we go to the 2-to-1 non-conforming grids, we don't know how to, we haven't tried, but we don't know, it's not immediately obvious if you can preserve the conformal, or the mimetic properties of the scheme. So then just a quick evaluation of the final mesh refinement strategy in the shallow water test case. Goal here is just to ensure mesh refinement does no harm to the global solution. Following the, and using shallow water global air norms, following the approach in a couple papers, Meeks and Sear et al. And Hillary Weller et al. And Todd Ringler et al. So I just want to look at mesh convergence rates with highly unstructured grids. And we're going to reproduce as closely as we can the Ringler 2011 results and look at the convergence as a function of the low resolution grid spacing for suites of refined grids. So this means, for example, the X8 grid, that denotes a level of 8x refinement. So we have say a 330 kilometer grid shown here with a factor of 8 refinement in this region. And then we have a suite of grids like this, just continually refined. So you can look at convergence with convergence of the 8x grid as a function of low resolution. And then repeat that for X4, X2 in uniform. So this is the normalized L2 error for the shallow water test case 2 geostrophic balance at 12 days, which is slightly longer than the original test case. And then there's 3 groups of data. The first is just for reference, is the spectral element method on a uniform grid running with no stabilization at all, because we can actually run all the shallow water test cases without any dissipation. And that's actually the only way to get the 4th order convergence rate, the formal convergence rate of the method. Once we add dissipation, and I have 2 types here, the convergence it reduces a little bit to about 3.5 and then 2.8. So the first family of curves is with the tensor hyperviscosity coefficient scaling with grid eigenvalue, the length scale to the 4th power. That's what you would use if you're using hyperviscosity only for stabilization of the method. And then the second group is the kind of operational setting that we use in CAM, where the hyperviscosity is also serving the role as to dissipate kinetic energy, to maintain a nice entropy cascade. So 2 groups. And then let's just ignore this one and look only at the set of grids that scale like the 4th power. Those are the circles. Their convergence rate's about 3.5, and they all do lie on top of each other. So you run the uniform one, which is the purple, then the suite of convergence sites with the X2 grid, X4, and X8 grid, and they all more or less lie on top of each other. So the introduction to refinement gives us no benefit, but does, in this case, no harm at all. In test case 5, just one set of data, and the refinement is actually over the mountain, so there is a teeny benefit to all the refined grids. But again, the introduction of refinement, and now the convergence is only second order and slowing down as you converge to the uncertainty in the reference solution. But again, the introduction of refinement doesn't hurt the solution in any way. So it's maybe a low bar to pass, but for the application we're looking at, it's an important feature. So the variable resolution works as one would expect it to. High resolution features are captured in the high resolution region. The mesh refinement does no harm to the global errors. And we were just recently funded to look at VMS instead of hyperviscosity, so that has a big advantage that the coefficient now doesn't depend on grid resolution but flow dependent. So it seems a much more sensible approach, and we've seen good results in continuous Galerkin finite element methods, including the presentation 2 days ago at this workshop. So thanks.
Other questions? Who?
Just a comment that your H to the 3.5 L2 convergence is pretty much consistent with what you'd expect from having a maximum error of losing one order of accuracy on the boundary, essentially. So it's that's what.
But I would not expect that, because with no viscosity, we don't lose an order on the boundary in L2 and max. And then the viscosity, the impact of it is decreasing in fourth order. So I would actually expect it to maintain fourth order. So you just add a term that's decreasing in fourth order. So I actually don't understand why we.
It may be some characteristic of the truncation error in the viscosity itself that's causing you to lose one order. But because it's a steady feature, it just sits there and accumulates error at that refinement transition region.
Other questions? Yes.
Yeah. So if you treat the tracer transport vertically differently, is the result going so bad that you have no choice but treating it differently in the vertical?
We treat them slightly differently, but then the dynamics, the mass is a surface pressure, not a 3D field. But you can write it as a 3D equivalent, 3D advection of delta P, and then the mean fluxes, horizontal and vertical, from that implicitly defined equation are what's used to affect the tracers, so it maintains consistency. Is that what you're asking?
Yeah, I mean, you use pineapple, if I remember correctly. Vertically Lagrangian for the tracer transport in the vertical.
Yeah, so in a sense, the dynamics, since it's hydrostatic, surface pressure, doesn't have a vertical transport. So it's actually perfectly consistent to treat the tracers vertically Lagrangian, even though the mass in the dynamics is not vertically Lagrangian.
You said model after chem FE doesn't mean you use finite volume.
Oh, so it's everything except the horizontal, which is spectral elements. Sorry, I misunderstood you.
Okay, I think we have to move on. Let's thank Mark again.